All right, so here we are with our fencing. We have 400 feet of material. One side of the fence is up against a wall, and so we have three other sides. We were told to make a rectangular enclosure. So that's our situation. We want to maximize, we want a maximum area. What shape should we build in order to maximize the area enclosed by this fence? So in order to do this, right, we know area is length times width. We're going to have to label some things here. So let's label some sides. Let's call this a Y. That means this is a Y. That's what rectangles are, right? Those two sides are the same. We can call this an X. And then we can say that the area is going to be Y squared, sorry, not Y squared, Y times X, length times width. So that's the area, that's what we want to maximize. This is, again, our objective function. That's what this is called. All right, so that's the objective function. And like in the previous example, it's a function of two variables, which is kind of a problem for us. We need it to be a function of one variable in order for us to take a derivative and find critical points. So how can we deal with that? Well, we haven't used the fact given to us in the problem statement that we have 400 feet of total fencing. So we know that 400 is going to equal 2y plus x. We're going to use up all of the fencing, right? So the two sides, the two widths plus the length is going to equal the 400 feet. We're going to use it all up. And from that, we can say x equals 400 minus 2y. And we can use that, we can substitute that into the area equation. So we will get A equals y times 400 minus 2y. Now that's a function of one variable. That's something that we can work with. That's 400y minus 2y squared. It's a function of one variable. At this point, this is just a problem out of section 4.1 in our textbook, right? We're just going to take the derivative, 400 minus 4y. We're going to set that equal to 0 and get 4y equals 400, or y should be 100. And if y is 100, that means x, well, let's double check that what we have here is actually a maximum. The interval here, the endpoints, you know, we could have y equals 0, which would give us an area of 0. We just have 400 feet of fencing spread out along our wall, which doesn't really make any sense. Or we could have x equals 0, in which case we would just have one long line of fencing extending away from our wall, which also has 0 area. So the end points of our interval give an area of 0. So those can't be our max. So the max has to happen at a critical point inside. There's only one critical point, which we found, and so this must correspond to our maximum. All right, so we can double check that that is a maximum using the second derivative test. The second derivative is minus 4, so this anywhere, so the second derivative at 100 is less than 0, and so what we have is a local max. So we have our local max. It's going to be our absolute max because the interval for y, the endpoints for y are y equals 0 or y equals or x equals 0. I guess we can say it easier that way. And both of those give an area of 0. So we can check the endpoints. The max or min isn't going to happen there. So the max happens here at y equals 100. If y equals 100, then x equals 400 minus 2y, so x equals 400 minus 2 times 100, so x equals 200. And so those are the dimensions that will maximize our area. The question asked, what is the maximum area, right? So the maximum area is 200 times 100 square feet. So that's 20000, 20,000 square feet with x equals 200 feet and y equals 100 feet. And that is our answer. And this was similar in a lot of ways to the previous example, but each example and each problem is going to feel a little bit different because you're going to have to come up with the right equations, find the objective function, figure out how to use the information in the problem to make the substitution that we want to make.